Okay, people. Wow. Look at all these empty spots. Well, I hope they're doing something useful. Huh? What do you think this is, buddy? Actually, it was interesting. Our polling station is right by, it's on the Clark Kerr campus, Redwood Gardens, where the senior citizens home and is. So it usually takes us like 2 minutes to get to the booth and vote. It takes 15 minutes to actually fill out the bubbles. There was one computer there. Nobody touched it. They avoided it like the plague. So everybody just filled out the forms and stuck into the scanner. And that was it. So you always have a paper trail in case something goes wrong. But that was that I thought was interesting. Nobody would go near the computer. All right. So we were talking about causality. There's a system F. We say the system is causal if it doesn't peek ahead into the input. In other words, past outputs, past and current outputs, and current output values don't depend on future input values. And a consequence of that, of this definition, that in order for the system to spit out the value for the current output, it doesn't have to look ahead into the future of the input, is that if you have two input signals, x1 and x2, that are equal up to a certain point in time, tau less than or equal to t naught, then the corresponding outputs will also have to be equal, because the system will not be able to distinguish between any two input signals so long as they're equal to each other. So if this property is true, if the above is true, for all x1, x2 that have this property, and so I'll put that as the input signal space, and all t naught, then the system is causal. This is all a fancy way of saying a system that doesn't look into the future cannot distinguish between two signals that are equal up to a certain point in time, and perhaps they will become different at some point into the future. So we had an example of this that we rushed through, so let's do that again. In this example, I didn't completely specify the system. I specified it partially. Yeah? No. It has nothing to do with linearity and time invariance. This definition is for any system. Right. But as we saw in this example that we did, and we'll go over that again, if the system happens to be linear as well, then it implies certain things in terms of the relationship between the input and the output. So let's see. We have a system that I'm characterizing with 3 pairs of inputs and outputs. If we give the system the input 1, 2, 3, so this is x1 of n, we get out the output 2, 1. If I give the input, if I give the system the input 2, 3, so this is my second input, I get out, at 0 I get -1, and at 1 I get 2. Okay? And all these signals are 0 where I haven't drawn any lollipops. And for the third input-output pair, I have an impulse at 4, and the corresponding output goes from 3 to 5, and it's 1, 2, 1. So this is a system. I've given you 3 input-output pairs. And I'm also telling you that this system is time invariant. Okay? So you essentially know 4 things about this system. That it's time invariant. That's one thing. That for this input, you get this output. Second piece of information. For this input, you get this output, and for this input, you get this output. So 4 pieces of information about the system. And the question is, can this system, well, I have several questions, but the only one that we can answer at this point are a couple. So the first question is, can this system be causal? And the second question is, what's the response, or can you figure out the response of f to the Kronecker delta? So what's the response to the impulse? Notice I'm very careful. I'm not calling it the impulse response because I reserve that phrase for LTI systems. And we don't know yet that this system, whether the system is or can be linear. In fact, that's the third question. Can f be linear? Okay. We addressed the first part, but we were rushed. So let's go over that again. Can this system be causal? Notice whenever I ask questions of this nature, I typically have a multiple choice question. Make the strongest statement you can make about the system. The system must be causal. The system can be causal. The system cannot be causal. Okay? Must be causal should be ruled out right off the bat, because I haven't completely characterized the system to begin with. So there's no way you can conclude that this system must be causal. So that's nonsense. You just cross that out. So the only two possibilities are the system can be causal. We don't quite know because you haven't completely specified it. Or the system cannot be causal. You've given us just enough information to conclude that it's impossible for the system to be causal. So what I want you to do is figure out if this system can be causal. And talk to your neighbors, and you can refer to your notes from last time if you want. This test cannot be used to prove that a system is causal, because there's no way you can, for a typical system, know what all the possible input signals are. How are you going to list all the possible discrete time, real value discrete time signals? You can't. So there's no way you can exhaustively go through those and know, on top of that, know what the corresponding responses are. So the only time you're going to use this property, or this definition of causality, is when you want to show that a system cannot be causal. Find two input signals that are equal up to a certain point in time. And of course, this can be also written in terms of discrete time signals, which is the example we have. Find two input signals that are equal up to a certain point in time, and show that the corresponding outputs differ even if at one point prior to that time. Then you're done. You've proven that the system cannot be causal. So see if you can do that with this system. You may not need all of the three input-output pairs. You may just use one or two of them. Which one of these questions is the easiest to answer? B. So let's do that. How do you answer B? What property do you use? Time invariance. And you exploit time invariance to shift which one? X3. So you use time invariance and shift X3. Which way? To the left by 4 samples. So when you do that, you get the impulse at the origin. So this is X3 of n plus 4 or minus 4? Plus 4. Going into the system. You know the system is time invariant, so the corresponding response is Y3 of n plus 4. So you correspondingly shift Y3. And when you do that, you get minus 1, 0, 1. Now, if I had, so this is the response of the system to the Kronecker delta. Sorry. If I had not made the lollipop here of height 1, then you would have been in trouble. You couldn't have used this, because I haven't told you that the system is linear. You could have only told me what the response of the system is to the scaled impulse. You could have still shifted it, but you couldn't have scaled it down, because I haven't told you that the system is linear. All right, so which one do you want to answer next? A. How do we go about doing that? Hmm? The response of the impulse, this one? Yes. Okay, so now compare, so let's call this X4. Okay. Up to and including -1. So let's be careful with the, so we note, this is part A, note Y4, X4 of n is equal to X1 of n for all n less than or equal to 0. Oh, yeah, they agree at 0. Sorry. But what? But you can't say the same for Y4 and Y1, because Y4 is 1 at -1. Y1 is not. Y4 at -1 is 1, which is not equal to Y1 at -1, which is 0. All you need is to show that the system is not causal, all you need is one pair of input signals for which equality holds up to a certain point in time, but the outputs differ only by one sample or more. Yeah, that's not going to help you. Yeah. That's why I said this can only be used to prove that the system is not causal. Just because you find a pair of input signals that agree up to a certain point in time, and their corresponding responses agree up to a certain point in time, doesn't mean that the system is causal. It just means that you've got to go back to the drawing board, pick another two input pairs. Or keep the same two input signals and pick another boundary point. In fact, in this case, you can change the boundary point and not to -1. Right? So x1 and x4 agree up to and including -1, and their corresponding outputs agree up to and including -1. Does that mean the system is causal? No. That's why I said both of these conditions, that x1 and x2 are any input pairs that you can find that agree up to a certain point in time, and for all boundary points that they agree with up to. This must be true. This must be true. So here, all we had to find was a pair of input signals that agree up to and including a certain point and not. And then look at the corresponding outputs, up to and including and not, and see if they differ at any point. And we did. At -1, they differed. And that's all you need to show that the system cannot be causal. So let's go to C. Can F be linear? Oh, so let's draw our conclusion here. Therefore, F cannot be causal. So you're saying F cannot be linear. How do we show that? Which x? I can shift x. Yeah, there's more than one way to show that this system is not causal. So one way was to look at this signal that we just figured out, this input-output pair. Another way is to shift x2 to the left by one sample. What happens when you shift x2 to the left by one sample? Up to what point do x1 and x2 agree? Till -1, right? Would the corresponding outputs agree up to and including -1? Where would they differ? At -1. So that's another way to show that the system is not causal. Yeah. Okay, so let's go to linearity. Who said it can't be linear? Ned.
So you can see that the input signal x1 is the sum of x2 and x4, but the output signal y1.
It's not quite the sum of x2 and x4. x2 is at 2 and 3, so you got to shift x2 before you can say that. So you're saying x1 is equal to x2 shifted by how much? One sample plus x4. Okay? Question. Is y1 equal to y2 n plus 1 plus y4 legitimate way of doing it? You'll end up finding that it isn't. Any other way that may be easier? No. The response to the impulse.
Okay, the response to the impulse.
Yeah. So how does that negate linearity. Wait. Well, let me get this straight. So y2 can never be created. Oh, I see. Okay, so you're essentially doing another modification of this. You're saying x2 is x3 is 2 times x4 of n plus 2 minus 2? Oh, x minus 2. I'm looking at the wrong signal. X n minus 2 plus 3x4 n minus 3, but y2n. Oh, I forgot to answer no here. No. But y2 is not equal to 2y4 n minus 2 plus 3x4 n minus 3. I'm still looking for a simpler solution. This is all too many manipulations of lollipops. Ali.
If you assume it's linear, then you know that the impulse has to be 0 for n less than 0. You can see that's not the case. For a linear time invariant system, the impulse response has to be 0 for n less than 0.
No. That's for an LTI system that's causal. Actually, this may have been the simplest one. It's for causality that I. Let's see. The first one was x2 and x4. That's a reasonably simple manipulation, so we can live with that. Yeah, I'd go along with the first solution, or alternatively, you can create x4. So you say x4 of n is x1 minus x2 of what? N plus 1. But y4 is not equal to y1 minus y2 n plus 1. Yeah, so there, except for this one, which involves too many multiplications and scalings, I'd say the first one and the fourth one and the third schemes are the easiest to do the manipulations on graphically. All right. Well, even now, I can use x3 and y3 to show that it's not causal. The easiest way to show that it's not causal is to use x3 and y3. How do I do that? If I assume it's linear. Suppose I changed this problem a bit last time. I said instead of assuming that this system is time invariant, assume that this system is linear. So we can't do this x4, y4. So forget that. You just look at, in fact, let's create another example with this. Here's a brand new example, okay? I have a system F, linear. And in response to the impulse at 4, I get, so let's call this x1, I get At 3, 4, 5, I get 1, 2, 3. So this is y1. The system is linear. Can it be causal? How do I show that? So in this system, in this case, I'm not even giving you 3 input-output pairs. I'm just giving you 2 pieces of information instead of the 4 in the other problem. I'm telling you it's linear, and I'm giving you an input-output pair. So how do I show that this system cannot be causal? Causal.
If you sort of add x1 and x1 to say to get an x2, they are equal up to 3 and 4. However, we generate a y2 by adding y1 and y1. At 3, they're not equal.
So you have the right idea. I just want to simplify it. So instead of adding this to itself, can you find another signal that you know satisfies the linearity property? Input-output pair. That's equal to this signal up to 3. Up to and including 3. But the corresponding outputs are not equal up to and including 3. Huh? You can scale. So you can obtain that signal by scaling this. What's the best scalar? 0. If you scale this by 0, what are you going to get? The all 0 signal. And the corresponding output, because I know this system is linear, must scale. In fact, I know that 0 input produces 0 output for any linear system. And what do you know about x1 and x2? But y2 at 2, at 3, is equal to 0, which is not equal to y1 at 3, which is equal to 1. So these two signals are equal up to and including 3. They're equal up to that point. But the corresponding outputs are not. This one in particular is different from 0. Yeah. I could. In fact, I think that's what we did last time. So you're seeing a couple of things. When I first introduced causality and I asked the question, can a certain system be causal? A lot of you immediately jump to this conclusion that just because the output signal starts before the input signal kicks in, it cannot be causal. And I gave you a counterexample to that. Namely, any system that takes, regardless of its input, it produces a fixed signal, say cosine omega naught n. Put whatever you want here. For all x in the input signal space. So I define a system that no matter what you give it, it's going to send it to /dev/null and keep this, spit this out. Okay? So this system is perfectly causal. It doesn't even have to look ahead into the future of the input. In fact, it doesn't have to look at the input at all. Right? So even if you give it an input signal that says an impulse, it's 0 for all the way up to -1, but the output is not 0 all the way up to -1. So this one is non-zero, even though that one hasn't kicked in. So you can't just use that argument to say that a system is not causal. This is a perfectly causal system. Causal system. Okay? Today's your day. Notice I'm not asking Meatball to pick anybody because I want you all to be relaxed today. All right, take your break. All right, folks. Let's resume. I want to also talk about memoryless systems, so we need to wrap this up. So in this case, we have a perfectly causal system. So just because the output is non-zero before the input becomes non-zero doesn't mean that the system is not causal. But if I tell you that the system is linear, or if I tell you that the system is time invariant, you can use that as a gauge of whether the system is causal. So let's go back to the linear system. Actually, we dealt with the linear system. So in this linear system, we have an input that becomes non-zero at 4, but the corresponding output becomes non-zero at 3. In other words, the output kicks in before the input kicks in, colloquially speaking. The moment you have a situation like that, you can use the 0 in, 0 out test to conclude that at the location where the input is non-zero, but where the output is non-zero, but the input is still 0, you have a difference. So in this case, we use the sample at 3, because that's where the input is still 0 at 3, but the output becomes non-zero at 3. So it cannot be causal. So this is actually a test that you can use. And I wrote this up last time as well. So if a system is linear and it is causal, then the output cannot precede the input. So L means system is linear. C means system is causal. P means output precedes input. In other words, it changes value while the input has not changed value. So if the system is linear and it's causal, then the output cannot precede the input. Logical equivalence of this, one logical equivalent that you can use is that if the output precedes the input, then this whole thing is negated, which means not linear or not causal. So at least one of these two properties is violated. And that's certainly true in the examples that I've given. I'll define what I mean by P, this precedes, a little more precisely later, in a few minutes, in fact. So what about time invariant systems? What if a system is time invariant, like in this example, and you have a situation where the output precedes the input? The input is 0 up to and including 3, but the output is non-zero at 3. So in fact, in that example, all I needed to use to prove that the system is not causal is the x3, y3 pair. So we have the situation where we have an impulse at 4, and that was x3, went into the system F, which is time invariant, and we got 3, 4, 5. 1, 2, 3. And this was y3. Okay? X is 0 all the way up to and including 3. But y starts kicking in at 3. So y kicks in before x does. To show that this system is not causal, all you need to do is shift the input signal to the left by a sample. So you look at x3 of n plus 1. And now the impulse will be at 3. So it's 0 up to and including 2. The corresponding response is shifted. And we know that because the system is time invariant. So it's a 2, 3, 4. And this is y3 of n plus 1. Let's call this y5, since we've already used 4. And let's use x5 for this. Now compare x3 and x5. They're equal up to what point? 2. x3 and x5 are equal all the way up to and including 2. But what about y5 and y3? But y5 at 2 is 1, which is not equal to y3 at 2, which is 0. So anytime you have a situation where the output precedes the input, and you're told that the system is time invariant, it cannot be causal. So not causal. And you can write a similar logical statement for time invariant systems, namely that I don't want to erase that, so let's erase this one. So if a system is time invariant and it's causal, then the output cannot precede the input. That's the other statement. And the logical equivalent of this is that if the output precedes the input, then the system is either not time invariant, meaning it's time varying, or it's not causal. Or it's neither time invariant nor causal. Okay? Yeah?
Are all linear or time varying systems causal?
No, certainly not. Why would all time invariant systems be causal? Here's a time invariant system.
What about all linear systems?
Nope. Here's, in fact, a linear time invariant system. That's not causal. This is linear. Linear and time invariant, but not causal. But determining causality for LTI systems is very straightforward, and we did this last time. Because for LTI systems, you know that the output is the convolution of the impulse response and the input. Right? That's the input-output relationship for an LTI system. The output is the convolution of the impulse response and the input. Well, write out the terms of this thing, and you'll have things like h of minus 1, x of n plus 1, plus h of 0, x of n, plus h of 1, x of n minus 1. Now, if you don't want any future values of the input to show up in the computation of the output at n, what do you have to have? What should be true about the impulse response? It's 0 for less than 0. the definition of causality becomes very straightforward for LTI systems. An LTI system is causal if and only if its impulse response let's call it H, is 0 for all n less than 0. If the impulse response has a non-zero value for negative samples, then the system cannot possibly be causal. Because in that case, a future value. So let's say in this case, H at -1 is non-zero. That means X at time n plus 1 is being used in the computation of the output at the current time. You can't have that. So LTI systems have this nice property. Now, before I wrap up this discussion and move on to memorylessness, I just want to make a comment about what I mean by precedes. If the input signal, what does precedes mean? It basically means that if xn is a constant for all n less than or equal to a particular value n naught, and y of n is equal to some other constant for all n less than or equal to n naught, then we say that yn does not precede. Then y does not precede x. In other words, as long as you keep x constant and y stays constant for that range of time, y has not preceded x. If y suddenly changes value in this range, then we say that y has preceded x. That's all it means. But typically 0, 0. These values are 0. Certainly for testing linearity and causality, all you need is for these values to be 0. But basically that's what it means. I mean, it's as long as your input signal is constant up to a certain point in time, and your output stays constant up to that point in time, then you say that the output has not preceded the input. If the output suddenly changes before the input changes, then you say the output has preceded the input. Yeah? Then you know it's not causal. That's exactly what this statement is. So you can construct variations, logical variations of this statement. Yeah. Okay. Now I want to say something about memoryless systems. This is the last of the important properties that we'll talk about. Actually, there is one other property called stability. We may or may not talk about that in this class. But for now, I want to wrap up the system properties, memoryless systems. Simply put, a system is memoryless. A system F is memoryless. Let's not label it for now. A system is memoryless if the output at t depends on the input only at t. So if this is my input signal, this is my system, and this is my output, if I can represent y at time t as a function of x only at that time and at no other time, then the system is memoryless. In fact, just to avoid confusion, let me just change this because this is a function that we'll look for. If you can find the function f, small f, that whenever you feed it x at that instant, it spits out the value of y at that instant, and the system doesn't need any other value of the signal, input signal x, then the system is memoryless. Instantaneous. So the systems that are instantaneous are memoryless. Yeah? That's right. No shifted values of x can show up in the output. No future values of x, no previous values of x can show up in the computation of y at the current time. So if t is the current time, I can only use x at the current time. Can you what? Well, I'm computing y at the current time. So how am I going to use y at the current time? No. It cannot depend on anything other than the input values at the current time. So a resistor is a very good example of a memoryless system. A resistor, you give it an input voltage, x, and you get a current. Y of t is x of t over r. So this is a memoryless system. Yeah? That's right. That's right. A memoryless system has to be time invariant by definition. And this is where the definition we give to memoryless systems differs from what you'll see in other textbooks. And that's something you've got to be careful about. So in our case, a memoryless system is time invariant. A memoryless system is also causal. Very good. This is exactly the kind of thinking I'd like you to do. Exactly. If a system is such that the output at the current time depends only on the input at the current time, or depends on the input only at the current time, then it obviously is not depending on future values of the input. So it must be causal. Is every causal system memoryless? No. So in fact, the arrows going the other way don't work. So going this way doesn't work. Going this way doesn't work. Yeah? That is not linear? Who can give me an example of a memoryless system that's not linear? X squared. Yeah. I never said this function has to be linear. Yeah. This is where we differ from other textbooks. Is this system memoryless? Very good example. Yeah, but your system needs to have an internal mechanism to keep track of time.
So you should say it depends only on the input at time, not depends on the input only at time. Because it could depend on other things as well. Like
Depends only on the input. Okay. Only on the input at t. Does that make you happy? Yeah. Okay. The problem with this system, so a system that has an output that is a function of time and x of t is not memoryless. But if you look at any other book, they'll tell you it's memoryless. So if you look at a typical book in signal processing, this system they'll consider to be memoryless. The problem with that definition, and they'll also consider systems like this to be memoryless. Modulation. According to our definition, this system is not memoryless. For the very simple reason that if you put this block here, this system needs to have an internal oscillator which must keep track of time. How are you going to make an oscillator without at least a couple of capacitors, or a capacitor and an inductor? Right? Each of those is a system that has memory. It stores information. It can. And no other value of the input. And no other value of the input. So let me draw this for you. I have a nice diagram of this, if I can find it. So we have a system it has an input signal space and an output signal space. The input signal space is the set of all functions that go from some domain to some range. So this could be, for example, the reals, and this could be reals or complex. Okay? The output signal space, for us to even talk about memoryless systems, the domain of the output must be the same as the domain of the input. So this would be, for example, reals. Or it could be, for most of us, for most of the examples we do in this class, we're either dealing with continuous time signals or discrete time signals. And it maps to some other range. Okay? Now, why is, we've defined systems as functions. So y in its entirety, the output signal y in its entirety, is a function of the signal x. I take x as a whole signal. I consider it as one marble in some bag. This is my bag. Small x is a marble in this bag. and my system says, corresponding to that marble, I give you this other marble in this bag. Okay? So if I give the system this input signal, it produces this output signal. At time t, this is what we have. Y at time t is the output signal, which is f of x, at time t. A memoryless system is a system where you can make this be equal to f at x of t. If you can find such a function f, then your system is memoryless. If you can find a function that relates your input to the output, where's my resistor? I erased it. So in the case of the resistor, I have a very simple function that tells me how the output relates to the input. Y at time t is equal to f of xt, where f of anything I give it is that thing over R. Right? And this is true no matter what the input signal is. I can't have different f's for different input signals. The same f has to work for all input signals. So if you can find such a function, then the system is memoryless. So a function like this, a system like this, y of t, is equal to log of square root of x squared t plus 1. Is that a memoryless system? Yeah, because that is the function. It only depends on the value of the input signal at t. Yeah? If you can't, then you either can say we don't have enough information, or if no single function exists, you say it has memory. Yeah. So now this definition of memorylessness has some ramifications, because if I have, for example, two signals, x1 and x2, that share the same value at some point in time, what can you tell me about y1 at t0 and y2 at t0? They must be equal, because the system at that instant in time cannot distinguish between these two signals. They both have the same value. You give the function the same value, it has to spit out the same value. You can't map the same input value to two different output values, right? And you can play around with this. So if you have a signal that is like that, where at t1 and t2, it is the same thing. So x of t1 is x of t2. At these two instants in time, this signal x acquires the same value. Then what can you tell me about the values of the output at t1 and t2? Huh? They must be equal. Because this system, when the time is here, t1, it has no idea what this signal is going to do in the future. It has no idea what it's done in the past. It only looks at the value at that point. Then time marches forward, and you get to t2. And the system is now here. The time is now here. And the system only looks at the value of the input at that instant in time. It can't distinguish between these two instants. It has to spit out the same value.
But it would still, even if we allowed
No. Because, so look at that example up here. You can have the same input value at two instants in time, but because of that n sitting in the front, they will be different. Okay, let's resume on Thursday.